Hello everyone, my name is Paul, and I'm the team lead for the EV Network Charger Simulator Capstone project. I worked alongside Zhihao, Sue, Jay, Katie, and Cameron. Our project was sponsored by Ranger EV. Ranger EV is a company that helps people charge their EVs by allowing hosts to list and manage chargers through their website. Our task was to develop a digital simulator of an EV charger, a tool that mimics how a real charger communicates with a central system that manages payments and charging operations. Our project was built around OCPP, the Open Charge Point Protocol, which is the industry standard for how chargers communicate with networks. Our simulator follows this protocol to send and receive messages just like a real charger would. And now, on to some demos.
Hello everyone, I'm Zhihao Wang, and for now I'd like to showcase an interesting feature of our charger simulator project, which is the exception simulation. This feature is designed to create a testing environment for the Sentry system when a charger encounters an abnormal situation. As you can see, we currently simulate 3 chargers and their current state is available right now. So you can simulate like start charging or stop charging normally, like it's preparing, charging right now, and stop charging. Now suppose we want to simulate an abnormal situation with the first charger. You can just click the large red Simulate Exception button, and this action opens a pop-up window for constructing the payload. In this pop-up, you'll notice that the connector ID and the error code are required, while the rest fields are just optional. The requirement for each field is determined by the OCPP specification for the status notification object. To keep the data valid, we use a drop-down list for the error code, so you can only select the approved options. And for the connector ID, we assume each charger has only 2 connectors, so there's only 0 and 1 here. Next, let's try to create a payload for the backend. So for this demo, let's try 0 for the connector ID and pick high temperature for the error code and select the current time and click the send message button. Okay, so you can see that we have successfully sent the payload and the charger state changes to the faulted, and the original start charging button become a clear fault button. So this tells the central system that there's an issue and it should take some actions. And finally, to return the charger to normal, just click the clear fault button, and the charger is then reset to available right now.
Hi, I'm Sue. I will be giving a demo of the gear button from the charger frame and the log messages for our software. On the right corner of the charger frame, there is a gear button. When we click this button, it will bring the users to a small form. And this form allows the users to configure 2 values in the configuration registry. One is the ID tag, and another one is the central system URL. In here, it shows us the default ID tag and the default central system URL. We can change the ID tag to a custom value, maybe current tag, and then click the update button. Now, everything is updated to the custom ones. We can also use the easy button to leave everything staying the same. And we click the gear button again. This still showing us the custom values. Now let's dive into the log message part of the front end. These log messages are the simulator send messages and receive messages. For each message container, it will show the most recent 50 messages. And the message on the top of the container will always be the newest messages. Additionally, it allows the users to retrieve the previous message by scrolling down the screen bar. Like these are all the old messages sent. Now I'm going to demonstrate how users send a message through the charger frame and get send messages and receive messages from the simulator. Here, we can click the reboot button in the second charger. After the charger booting up, we can see there is a boot notification call type message element in the send message container, and there is a boot notification response type message element in the receive message container. If the user would like to retrieve more information about the boot notification call message from the send message container, we can just click it, and then you can see the hidden information such as message ID, charger point vendor, and charger point model, etc. And these are all the hidden information for the boot notification from the send message container. And for this correspond boot notification message from the receive message container, we can see the hidden information from the receive message container. We can see the hidden information such as the message ID, the status, the current timestamp, and the intervals. And that concludes my demo portion of the video.
Hello, this is Paul again, and I'll be discussing some of the motivations behind our project. Currently, Ranger EV conducts their testing using physical chargers. While this works, it comes with several challenges. Setting up a physical charger for testing takes time, space, and effort. If Ranger EV wants to test multiple chargers, it quickly becomes costly and impractical to maintain several physical units. Additionally, some charger features are hard to test in real hardware. For example, simulating rare errors, testing network failures, or experimenting with load balancing. These kinds of tests require precise control over the charger's behavior, which can be difficult to achieve with the physical device. Our solution was to create a digital EV charger simulator. With our simulator, Ranger EV can test more efficiently without needing real hardware. It allows for controlled, repeatable testing, making it easier to debug issues and develop new features. The simulator also enables them to scale their testing, simulating multiple chargers at once without additional hardware costs. By providing this tool, we help Ranger EV streamline their development process and improve the reliability of their EV charging system.
Hello, my name is Farhan, and I will be going over the top features of our project. So there's three major features, which the first one is simulating a vehicle starting a charge. Then we have simulating a vehicle ending a charge and view recently logged messages in the user experience. So first, before we can start charging, several things have to happen first. At the very beginning, a WebSocket handshake has to occur where we need to establish a connection with Ranger EV's backend and our charger. Then a boot notification is sent to register the charger with the backend. A boot notification just gives our hardware information to the backend. Then a status notification is also sent here to update the backend on the charger's availability. And finally, an authorized message is sent. Once the authorized message is accepted, then we can begin charging. So once we're charging, we first send a start transaction message. This tells the backend the connector being used for charging, the ID of the user or vehicle initiating the session, a timestamp of when charging started, and the total energy consumed by the charger before the new charging session is started. Once charging, the charger sets electrical values for a new charging session. A meter values message is also sent periodically to the backend to report energy consumption. Then when we end charging, a stop transaction message is sent. This sends a transaction ID, a timestamp of when the charging completed, and total energy consumption in kilowatt hours. Then electrical values of the charger are zeroed out. Some additional features we have are taking a charger offline, throwing an exception error, simulating 3 chargers at one location, and updating a charger's configuration. So future features we didn't end up getting to implement. The first one is load balancing. Load balancing is a way to evenly distribute power amongst multiple chargers. This is really important because if one charger has higher voltage than the others, it can end up reducing the amount of voltage they can output. And also, if all of the chargers have a higher voltage combined than the circuit they're on, that can cause a physical breaker to be tripped. Next, we have simulate any OCPP message. It's important to note that in our project, we have a subset of all OCPP messages, and there are a lot more that we didn't have time to implement. And lastly, simulating a physical breaker being tripped. This entails when a physical breaker is tripped and power is lost, then the charger needs to respond once power is back. They usually do this by sending a message to the backend and alert that a faulted state occurred.
Hi, my name is Catherine, and I will be talking about the architecture and design of our project. Our project is composed of a front-end and back-end system, which communicates through a simple REST API. The front end is a basic user interface, which will allow Ranger EV to operate their simulated charge points, while the back end contains the main guts of our simulator and communicates with the Ranger EV backend. Moving on to the front end components. The front end consists of two parts, the user interface, created in React, and the HTTP client. These together allow you to configure and interact with the various charge points in our simulator. The backend is where the main bulk of our project is. This starts with an HTTP server. This server provides the REST API that the front end uses to configure our various charge points within our simulator. The state machine controls and handles the various states in our simulator, such as charging, booting up, and available. The message scheduler manages the ability to send scheduled messages from our simulator to Ranger EV's backend. As we continue to the backend components, we have the message queue, which stores and handles the sending of our OCCP messages. Next is the WebSocket client, which communicates with the Ranger EV backend to pretend to be a charge point on their network. Lastly, we have the message handlers, which handle responding to messages from Ranger EV, updating the state in our simulator, and providing the required call results back to the backend.
Hi, my name is Jay. This is how we developed front-end and back-end components. Our team split into two teams, back-end and front-end team. We use the Agile software development method, and we use Git for the version control system, and we use Jira for project management. On Jira, we set a certain requirement for each sprint to reach the sponsor's requirements. And we had a regular stand-up meeting twice a week. Responsibilities and contributions. And Paul is the project lead. He oversees the backend and frontend and code refactoring, and organizes over projects and meetings, as well as meeting with sponsors. And he reviews and gives feedbacks on GitHub pull requests. And Katie, she implements OTPP WebSocket clients and message scheduler, and she manages message timeouts and error handlings. And Cameron, he implements authorization process and electrical transition and charging profile functionality. And Jay, myself, I implement charger state machine and start and stop charging functionality. And Sue, she implements charger UI and improved UI accessibility and setup for front-end testing. And Zhihao, he implements UI components and trigger messages functionality and standardized CSS. And we had some unexpected events. Our GitHub actions are failing due to spending limits. So we tried to purchase GitHub Pro to solve it, but it went back to normal after like an hour. And we found out we have some unsupported messages that were not handled by our system when we connected to Ranger EV's backend for the first time. So we had to add some extra messages to handle. Lesson learned. We could be able to learn general knowledge of front ends and back ends development. Also, we could learn general understanding of how front end and back end interacts, and we could learn about importance of communication. When two tasks are interdependent, having a clear and consistent communication leads to the more efficient development process. And when someone is struggling, the best way forward is to ask for help and offer support for a better outcome.
Hi, this is Paul again. Brian Boucher, our point of contact at Ranger EV, has provided our team with a video giving us feedback. We'll play that now.
Hi, my name is Brian, and I'm the head of operations for Ranger EV, a startup here in Portland, Oregon. Along with the head of technology, Brandon, we were the clients of this team's project. This is our second Capstone team with the Portland State CS program, and again, we're extremely happy with the team's performance. Paul, Cameron, Shuhua, Catherine, Jay, Zhihao, they all did a great job internalizing the project's requirements and delivering a great result at the end of this project. We tasked the team with creating a simulator for our EV charging network. The simulator would simulate all of the network connections that an EV charger in the real world would be able to make and respond to, thereby creating a digital twin of the physical hardware that we interact with on a daily basis. The hope was that with this simulator, we would be able to accelerate our ability to test new functionality without the need to interact directly with hardware and charging infrastructure for our initial proof of concepts. What impressed me the most about this team was their ability to extrapolate from the documentation provided, creating a fully functioning simulator with very little input from Brandon or I. They basically had our requirements and the documentation from the Open Charge Alliance, which told them how a charger should react to messages. Many of the commands that we had them implement, we hadn't actually done ourselves, so it was great to see the team's ability to self-actualize around the proper commands just simply from the documentation. Overall, the team's communication was very high and detailed, led through the team's lead, Paul. He did an excellent job keeping Brandon and I informed and calling the necessary meetings to showcase progress or get clarification on requirements as the situation presented themselves. The team seemed overall very strong and well balanced in terms of skill sets. It was nice to ride along with the team's code reviews, such that Brandon and I were able to keep abreast of changes and see how the team was implementing various features. Although we weren't monitoring it specifically, it also gave us a general sense of the team's velocity and pacing. As a student project, we got to see a lot of the pull requests happening on nights and weekends. As previously mentioned, the team did an excellent job in encapsulating all of our requirements into the finished project. We were also able to work on some of the stretch goals by the end of the project, which was great to see. I haven't gotten a chance to review the final documentation as of the date of this recording, but I'm sure based on the other artifacts they've created, it'll be high quality as well. The last ask that I've had to the team is to make sure that this project is documented well enough that someone like myself, who's not a full-time developer, could extend and support the system without too much review. I don't have that many critiques of the team. Although we had a great relationship with Paul as the team lead, we would have loved to hear more distinct voices from the team overall. I would just personally encourage folks, even if there is a dedicated leader, to find and make space for themselves to present individual aspects of the project, especially if they had a large hand in creating them. Our project also included a user experience, and although this was an internal tool, I would have loved to see someone take it upon themselves to have some fun styling it. This was neither an implicit or explicit ask, so it's not a surprise, but more of a recommendation that there's always opportunities to integrate, small amounts of fun or whimsy into development projects and impress clients, even if they end up rolling back some of the more wild stuff. One question we haven't gotten to ask the team, but something that in this age that we're living in is quite important, is what use of, if any, was AI used in developing or improving the code that was generated as a part of this project? It would just be interesting to know the answer, and I'm planning on asking that to the team before the end of the project. Otherwise, I want to thank the team for their efforts. It was a very enjoyable experience being their client, and I'm impressed with the outcome of their development. I wish them all the best on completing their program and starting their future careers as software development professionals. Thank you very much.
Our simulator is public and accessible at the link shown on this slide. Instructions for building and using the simulator are stored in the repository. Before we wrap up, I'd like to take a moment to make some acknowledgments. First, a huge thank you to Brian Boucher and Brandon Gallagher at Ranger EV for sponsoring this project and giving us the opportunity to work on a real-world challenge. I also want to thank our Capstone advisor, Bruce Irvin, for his guidance and insight throughout the process. To my teammates, thank you for your hard work, dedication, and collaboration. This project wouldn't have been possible without each of you. Finally, thank you, viewer, for your time and interest in our project. We're excited about the impact the simulator can have, and we appreciate the opportunity to share our work with you today.